The topic is quantum and quantum-inspired evolutionary algorithms for optimization, and the work that I am presenting is joint work with Faulkner Saulen and Professor Aman Srivastava from CIU Kiel, and my students here, Ashish Mani, Apurv Narayan, and V. Prem Prakash. Our focus is on optimization algorithms, and we are looking at both quantum and quantum-inspired algorithms. The general optimization algorithms can be then classified into two parts. We could be talking about combinatorial spaces, or we could be talking about real parameter function optimization. We already had a lot of discussion on Grover's algorithm, but the whole idea is that the complexity is square root of n. So if we are talking about a combinatorial algorithm where you are dealing with exponential search space, square root of n would still be exponential. But people have used Grover's adaptive search for unconstrained continuous global optimization by discretizing the continuous space and then trying some algorithm which uniformly, in a uniformly distributed space, it improves the region of the previous solution. And then this improving sequence is shown to converge to global optimum. But then you need to know a priori the number of rotations before this measurement can be made with probability of success. We just had a presentation which talked about adiabatic quantum algorithms, so I am not repeating that. So essentially what we are trying to do is, we are trying to do constrained optimization problems using adiabatic quantum algorithms, and the idea is that we already had some algorithms which have been presented by, for example, Fari, where you are searching for a marked element in an unstructured database with n elements using the global version of adiabatic theorem, and that has a running time of order n. But then by adiabatic version of Grover search, which has the same complexity as the circuit model, Roland employed local adiabatic evaluation, and this approach was used for continuous constrained optimization problem, and you get the same speed up, which is order of square root of n. In our work, we are integrating ideas from Grover search algorithm for finding minimum and adiabatic quantum computation through local evolution to achieve quadratic speed up for solving continuous domain constrained optimization problem. The big advantage conceptually is that you do not require a priori knowledge of the number of optima, and then there is no fear of overshooting the optima, as these are represented as the ground state of the problem Hamilton. So that's essentially the algorithm that we are working on. We're still at a very nascent stage, and we have sent this to this particular conference to get the feedback. But then, in combinatorial optimization problems, as well as for real function, where your search spaces are large, order of square root of n is not really good, because your search spaces are too large. So, and as has been pointed out, there are two communities, one which believes that quantum computers are 20 years away, and the other which doesn't. But I think we need also a third community which says that, okay, let's not wait for quantum computers to be developed or for the majority or the minority to be proved correct. Why can't we use quantum-inspired ideas, just as people have used ideas inspired from brain to develop neural networks, and develop quantum-inspired evolutionary algorithms which use the ideas from quantum computing but are still classical algorithms which you can run on computers like this. And what can we do with those algorithms? So we have been working on this line of thought for a long while now, and I will show you some of the work that we've done in this particular domain. The basic genetic algorithms framework is that you have a population of points, and then you have some operators which you evolve the population with, and then develop new solutions and try to use the ideas from nature which evolves better individuals through a slow process of evolution and solve combinatorial optimization problems. But the problem is that although nature has been successfully doing this, and there's a question mark as to whether it has really managed to evolve intelligent species, but yes, we do believe it has. But for optimization problems in engineering and other real-world applications, is this fast enough? To solve real-world optimization problems fast enough, you need to design evolutionary algorithms for each particular problem, and that's an art. That's not really a science as of now, because we want to ensure reasonable computation times, and we also want to ensure that the whole search space is searched and we don't leave out any potentially good solutions. And we already said that the search spaces are really large in these problems. So how do you satisfy these mutually conflicting requirements? That's the idea. So the fundamental problem with evolutionary algorithms is that a good solution has only one chance to prove itself and generate good children. Otherwise, it faces the danger of being lost in elitist implementations. And we need elitist implementations because we want fast convergence. With this kind of probabilistic implementations, this can really happen because only one gene value may be improper and you might have a very different solution. So, people have talked about now estimation of distribution algorithms, where the algorithms use a probabilistic model of promising solutions to guide further exploration of search. And these can avoid the disruptive effects of genetic operators in evolutionary algorithms. Compared with traditional evolutionary algorithms, their behavior is easy to study and it's possible to learn and explicitly utilize the problem structure, as Dr. Tulsi was pointing out in the last lecture. If we can really exploit the structure, we have benefit of faster convergence. So this is the EDA framework. You have a population, you have a parent set, just like in case of genetic algorithms, but you have a probabilistic model which you're going to sample and develop new solutions, instead of just having genetic operators. The quantum-inspired evolutionary algorithms are probabilistic, population-based evolutionary algorithms, borrowing concepts from quantum computing. But the reason I digressed a little towards estimation of distribution algorithms is that QEAs can also be understood as multi-model EDAs. So you're dealing with multiple models of the parameters together in a single quantum-inspired evolutionary algorithm. And that's the power that they give you. So this slide shows that although the ideas are developed from quantum computing, you're going to actually run them only on a digital computer and not on a quantum computer. So they are classical algorithms. And the essential difference is that here they are both population based, but in the quantum inspired evolutionary algorithms, you employ observation of qubit strings and quantum operators instead of the regular genetic algorithm using genetic operators. So once we have the qubit representation, to this audience I don't need to explain this. The good thing is that you have just one individual with the respective probabilities and it represents the whole state space with some probability of getting every possible point in the state space. And that's the power, because any individual in the search space is potentially obtainable through the collapse operation of just one quantum string. With that, the advantage is that you can deal with small populations in the quantum-inspired evolutionary algorithms, and that reduces the total amount of computation that you have to perform. Typically, genetic algorithms use large populations in order to exploit the complete search space, and that increases the population. Here, because of this ability of quantum representations, you can deal with small populations and reduce the computation. For the more computer science oriented people here, there is a link to the standard randomized rounding ideas that computer science gives you. Your basic randomized rounding is that you have the probabilities and then you do some k independent trials with these probabilities and then take the best solution out of them. In the QEA update and rotation, it is just like the sequence of randomized roundings that you do in the traditional computer science, but the advantage is that here you favor the probability distributions that encourage search towards the best so far solution. So it's randomized rounding with some kind of learning built in, and that improves your convergence. That's the way we can understand quantum inspired evolutionary algorithms very nicely. But then the big question is, how do you build the right amount of randomness in the algorithm? We need some amount of randomness so that we go to the different search spaces very quickly and exploit the ones that give us better solutions, but we can't have too much of randomness, otherwise it will boil down to random search. So that's the crux of designing the quantum-inspired evolutionary algorithms. How do we build in the right amount of randomness? So we've implemented some of these ideas for different problems, and I'll just show you a couple of examples. One is the quadratic knapsack problem, which is NP-hard, and it arises in a variety of applications. And we've compared the performance of this kind of randomized rounding with learning that QIEA provides us with implementations of the evolutionary algorithms, the naive EA and the greedy EA, which probabilistically favors objects with higher value densities. And this is the overall structure of our quantum algorithm. We start with a greedy solution and initialize the qubit strings in accordance with the greedy solution, which means that the probabilities of getting a 1 is more where there is a 1 in the greedy solution and 0 where there is a 0 in the greedy solution. So we are already biasing it towards the best greedy solution that we have already obtained. And then we apply the quantum neighborhood operators that we have designed and go through the evolutionary algorithm iterations. We tested this on 100 and 200 object benchmark instances taken from literature and compared it with the naive EA and the greedy EA. The QEA is able to hit the optimal solution 492 times in 500 trials. For 100 object instances, this comes down for 200 object instances to 482, but that's still much better than the EA implementations.
So these are the related publications from this work.
This is another problem that we are attacking with the help of these QEAs, which is the discrepancy of two colorings of hypergraphs of arithmetic progressions. Basically, hypergraph is a generalization where each edge could be any subset of the vertices instead of just two vertices. And hypergraphs of arithmetic progressions are the hyper edges, in which each arithmetic progression is a hyper edge. So your A, D and L are elements of N. So if you are having a hypergraph with N vertices, you could take all combinations of A, D and L from 1 to L minus 1, 0 to L minus 1 for I, and start with each possible A and D. So that gives us the number of hyper edges would be n squared log n. This number is important because I'll just show you how big the search space becomes. And how do you compute the discrepancy? You have a finite hypergraph and now you are coloring the vertices of your hypergraph, and the colors could be just two colors, minus 1 and plus 1. And the hyper edge is just a subset of vertices. Now chi E is the imbalance of the two colors in each hyper edge, and the discrepancy of a single coloring is the maximum of the imbalance over all the edges. And since your number of hyper edges could be 2 to the power n, and in the case of arithmetic progression it is n squared log n, in general it could be 2 to the power n. So if you are dealing with, say for example 10,000 vertices, you are already looking at a billion hyper edges. So if you want to compute the discrepancy of a single coloring, you need to look at the maximum of the imbalance of the colorings of these billion edges. And your problem is to find a coloring that minimizes this discrepancy. And if there are 10,000 vertices, there are 2 to the power 10,000 possible colorings. So that's the difficulty in the problem. Each computation involves a billion edges if you have 10,000 vertices, and there are 2 to the power 10,000 possible colorings over which you have to minimize your discrepancy. And since this is discrete, you won't have any gradients to guide you anywhere. Rules of thumb are very, very hard. Even if I change the coloring of one vertex, I do not know what happens to the discrepancies. Which edge will now have maximum discrepancy is very hard to predict. And that makes the problem really hard. So we had some theoretical results. Lower bound was given by Roth way back in 64 as n to the 1/4, and they have showed that this was asymptotically tight. But the question of actually finding such a coloring with this lower bound remained open, although the bound is there. So we took that as a challenging benchmark problem for investigating our algorithmic advances. The simplest is probabilistic half-half coloring. We just flip a fair coin to decide the color for each node in the hypergraph, and it can be shown that there is a discrepancy bound of n log n to the 1/2 by using this probabilistic method. Sarkozy came up with the algorithm which for 35 years had the best performance, and this gives a true coloring, that is n log to the 1/3. And the way it works is that it determines a prime number p and then uses that and uses the Legendre's polynomial to determine the colorings of the other vertices. I'm not getting into the details of Sarkozy's algorithm. Now what we have done here is, and that's the good thing about EAs, that you don't have to fight them, you can join them. We start with the best coloring that Sarkozy gives, and then try to improve the colorings by a massively parallel implementation of the QEA, and we use 96 processes, and we have also designed some local operators to guide the search. Now the results are interesting. In all these cases, we have started with the Sarkozy coloring as the starting point, and then used randomized rounding. But in order to keep the comparison fair, what we've done is, we've kept the total computation time that we give to each algorithm. Sarkozy has very little computation time, but randomized rounding and the kind of randomized rounding with learning that we are implementing, we take the same computation time. And there, the randomized rounding, since it doesn't do much of computation, it can try many more trials than the evolutionary algorithm. And we take the best solution that we get out of all these trials and return that as the answer. Now what we see here is that for 20,000, for example, the Sarkozy coloring returns 50. That is improved by the randomized rounding to 45, and we just noted the discrepancy obtained after each 25% of the computation is over. And the QEA is able to further reduce this to 43, and it is able to reduce this pretty quickly with 96 processes. Even with 25% of the computation time, it's already better than randomized rounding after the 100% computation time. So we thought, we got greedy. We thought, why should we use 96 processes when it's doing in 25% of the time? Maybe we can do with lesser computation. And it was really found that we didn't even need those 96 processes. In 16 processes itself, we are able to get to the same solution. So we also compared the performance with a classical EA. Maybe the EAs work well in this problem. It doesn't have to be a quantum-inspired EA. And so we did a parallel implementation of a classical EA and compared the results with the quantum-inspired. The classical EA doesn't get that kind of performance. It's not able to find those solutions. So there is something here, the randomized rounding with learning, that quantum-inspired algorithms are doing, which is leading them to better solutions. And we also tried to do some local checks as to whether it is at least locally optimal in the basic operations, and we found that yes, indeed it is locally optimal under 3 basic operations. If we change the color of one vertex or do some things like this, then the solution gets worse. So at least it's locally optimal. Obviously, we're not able to prove anything regarding the global optimality. So what does this tell us? There's now a budding interest in what is called as algorithm engineering, and the algorithm engineering says that hitherto the theoretical computer science people have always given computational complexity results, and the practical people have just concentrated on giving algorithms that give practical results on problems. They were not able to prove anything about optimality of their results, and these theoretical computer science people were getting some bounds that used to be very far away from the results that the practical people were giving. So now what we can do is, we are looking at Roth's computation of the lower bound constant and the Spencer's computation of the upper bound constant. We see a gap there and we know that this gap can be filled, maybe by better analysis. So the practice is now inspiring the theory. It could be both ways. Theory could inspire practice and practice could also inspire theory. Since we have been able to improve the results, maybe we can improve the analysis. That's the idea. And prove something better. So that's the graph that shows. And I already showed you that for 10,000, we're talking about a billion edges. So you can easily calculate how many edges are there in the hypergraph for 20,000 vertices. And now this, with further work, we are able to go up to now 1 lakh. I don't have the final results, so I'm not able to show you. 1 lakh is 10 power 5. So we are having results up to graphs with 10 power 5 vertices. So the final message is that these are competitive for search and optimization, and as long as we don't have a quantum computer, we don't have to really sit tight and worry that we don't have a quantum computer. We can deal with quantum inspired algorithms for solution of practical problems, and they do give us some good results. So we have also implemented real parameter versions of this, and I'm not getting into details of these. So real parameter versions for engineering optimization problems. Ashish is here, that's part of his PhD work. So this is the kind of work that we've done on engineering optimization problems. And also on power system problems, this is the work of G.S. Shailesh Babu in his PhD. So these can also be utilized not only for combinatorial optimization, they can also be utilized for real parameter function optimization. That's the message that I'm trying to give you. An interesting problem, I'll just take a couple of minutes to introduce this problem. And this is on studies on large-scale natural systems. Future Ocean Project is a project of the German research cluster that's being done at Kiel, with whom I have a collaboration. And there they're studying the ocean uptake of carbon dioxide. The model consists of a huge set of partial differential equations that have to be solved simultaneously. And our problem was to do the parameters estimation. And we have utilized these quantum inspired evolutionary algorithms for solving this Prem Prakash is also here, one of the students. So we have also implemented these quantum inspired evolutionary algorithms for parameter estimation problem in this model, where you are solving a set of partial differential equations simultaneously. And here we have used a hybrid algorithm because quantum evolutionary alone was not sufficient. The good thing about these is that you can add components as and when you need them. So we have added the standard automatic differentiation procedures that classical maths provides us, along with the QEA, and that has given us a fairly good solution. And the good thing is that this quantum inspired algorithm that we have implemented, it converges to the same solution in a couple of hours as the solution obtained by another group in UK, which takes a week of computation time. So that is pretty good. But the problem is that this is still not giving us an error of 0. Once we have estimated the parameters, we can do the prediction of the parameters and match with the data obtained. And when we do that, we are not getting an error of 0, which even the other group also independently working is not getting. So either there is a problem with the model itself. So the ocean people who have developed the model, they are now looking at the model and seeing whether some parameters have been missed out, and this model needs to be extended. So this is in this you have the details of the work that has been done in this context. And thank you very much.
We have time for questions.
In the first part of your talk, you said that this genetic algorithm approach to solving this optimization problem, we're looking for a quadratic speed up of that using quantum computing.
Yes, we are trying to speed up genetic algorithm performance, and we're using quantum inspired ideas for it.
But then can't you use quantum amplitude amplification for that?
No.
Why?
This is Still in the genetic algorithm framework, we are using iterations, all right, but the kind of rotations that we are implementing, they are to be implemented on a classical machine. So we are not really, they are quantum inspired operators, all right, but once we start implementing actual quantum operators for which the simulation itself will become very expensive, then computation will go out of hand.
Sir, your evolutionary algorithm, how close it is to the algorithm which can run in polynomial time, or can it be done a little bit closer to the polynomial time? Is it possible?
Okay, so the computation that you are going to expend is something that you can decide by implementation and limit it to some kind of polynomial, as we have done here. I showed you that we are using the computation time that's proportional to n square log n, because that's the number of hyperedges that we have in the graphs that we are dealing. But once you say that, you have absolutely no way of guaranteeing anything regarding the result. The whole problem with this area is that evolutionary algorithms have been shown to work. There is a huge amount of literature available on all kinds of practical problems, but the moment you start talking about proofs, they aren't any. In fact, there is a no free lunch theorem which says that any evolutionary search is as good as any other search when it comes to solving all problems. But the good thing here is that you, as was pointed out in the last talk also, you never look at an evolutionary algorithm as a cookbook which satisfies all kinds of search problems. We implement an evolutionary algorithm for a particular problem at hand, look at the structure in the problem, try to get the best possible solutions. To that extent, it works. The moment you say that, okay, I'm going to take this as a black box, apply it on another problem, you have no way of saying what would be the performance on that problem.
Thank you.